Hello, this is Richard Hammack's Calculus 1 course. We are in part 4 of the course on applications of differentiation. Today, lecture 34A on optimization problems. We'll break this into 2 lectures. Today, the first installment, 34A. Next, we'll do 34B. Our goal here is to take everything we've learned about absolute extrema and put it to work solving practical, real-world problems. I should mention that if you go on to a career that uses calculus to solve real-world problems, the kinds of problems you'll be working with are much more complicated than the ones we'll start out with today. But we have to start somewhere, so we'll start relatively simple. And for that reason, some of the problems that we look at may seem a little bit contrived and artificial, but they're great practice. That's our goal for this section. Apply what we've learned about max and min to practical problems. We're going to wade into this with a fairly simple problem. I want you to imagine that you're in this situation. You have 200 feet of chain link fence, and what you need to do is to enclose 3 rectangular regions like this. So you have a rectangular region divided into 3 pieces, and your 200 feet of chain link fence is going to be entirely used up to enclose this along with these 2 dividing lines. So the question is to find the dimensions of x and y that maximize the total enclosed area. Now, before we talk about a solution to this, I want you to just think about ways that you could build such a rectangular region enclosed by a fence. One way to do it would be this. You could say, well, I'm going to do my rectangular region 80 feet long, and so there you used up 80 feet of chain link fence, and there's another 80 on the top, so that's what, 160 feet so far. And then you're going to have 10 feet wide, so you have 10 feet, 10 feet, 10 feet, and 10 feet, and there you've used up all of your 200 feet of chain link fence, and you enclosed an area of 80 times 10 equals 800 square feet. On the other hand, you might think about doing it this way. Maybe make the length of the rectangular region 60 feet and the width 20 feet. And here, how much fence have you used? Well, 60 feet on the bottom, 60 feet on the top. That's 120 feet, plus another 20, 20, 20, 20, and that uses up all of your 200 feet of chain link fence. And you've now enclosed an area of 60 times 20 equals 1,200 square feet. And that was better than what we had over here. So the question we're trying to answer in this problem is, what's the best you can get? What is the greatest volume that you could possibly, or greatest area you could possibly enclose using up all 200 feet of your chain link fence? Is 60 feet by 20 feet the best? Or could we do better than that? What's the best we could do? Let's think about that. I've restated the problem up here at the top. You've got 200 feet of chain link fence to enclose 3 rectangular regions as illustrated, and we want to find the dimensions x and y that maximize the total enclosed area. In other words, we want to maximize the area A, which is x times y. Now, the problem with this is, we know how to maximize functions of a variable x, but this is not just one variable. Area here is x times y. So it's kind of hard to say what a derivative of that would be. It doesn't look like, it's not a function of x, so we can't apply our techniques for finding max and min to it. But we can resolve that by noting that there is a certain constraint in this problem. You have to use up all 200 feet of your chain link fence.
So the x here and the x here, which is 2 times x, and these 4 runs of y feet of chain link fence, which is 4y, that has to add up to 200 feet. You have to use up all of your 200 feet of fence. In building this region, this rectangular region. So you get 2x plus 4y equals 200. So x and y could have lots of different values, but they have to obey the rule 2 times x plus 4 times y equals 200. And you could solve for y. Getting y by itself, you get 4y equals 200 minus 2x. Divide both sides by 4. Y is 1/4 200 minus 2x, or just y equals 50 minus a half x. So here's an idea. We wanted to maximize area xy, and we said that's a problem because that's not a function of x. Well, now we figured out that y has to be 50 minus a half x. So we could plug in 50 minus a half x for the y right here, and we've got a function of x. Let's try that. So to summarize, we need to maximize area A equals x times y, and we just set that's x times y, which is 50 minus a half x. So we have x times 50 minus a half x. Multiplying that x in there, we get 50x minus a half x squared. So our area depends on x. It's always whatever x is, the area of that enclosed region is 50x minus a half x squared. So we can rephrase this question in terms of the language we've been using for Chapter 4. We need to find the absolute maximum of this function a of x, which is area, which equals 50x minus a half x squared. We'll call this 50x minus a half x squared, that function that gives area, just call it a of x. So we want to maximize a of x equals 50x minus a half x squared. And what interval are we talking about? Well, x, first of all, has to be positive, since it's a length. So we have an open interval starting at 0. But then how big could x get? Now, remember, whatever x is, however many feet of fence you use here for x, you got to use it again up there. So since you only have 200 feet of fence available to you, x can never be bigger than 100. It's got to be up to 100 here and up to 100 there to give you your 200. So your interval is the interval from 0 to 100. X is in that interval. Suddenly, this is looking like a problem from the previous section. We have a function we want to find the maximum of on an interval. So we know how to do that. We know that the first thing we want to do is find the critical points of our function. Now the interval is from 0 to 100. I'm just going to put that right down there. And let's look for our critical points. We start off by taking the derivative of area, a prime of x, the derivative of this function that we want to maximize, and it's 50 minus x. And wow, that's so simple. It's going to be easy to find the critical points there. There are no values of x that make that derivative undefined, so we look at what values of x would make it equal to 0, and it's just x equals 50. Our critical point is x equals 50. So let's put that down there. So the next thing we want to do is look at the sign of the derivative, because we want to apply the first derivative test to see whether we have a local max or a local min. So a prime of x is 50 minus x. And you can see here that as long as x is less than 50, 50 minus x is going to be positive. When x is greater than 50, 50 minus x is going to be negative. So we put those signs in there. And that means our function for area, a of x, it was increasing where its derivative was positive, and then it started to decrease after 50. So the area function, if you graph it, looks like this. It goes up, reaches a high point at 50, and then it goes down. And you can see from this that we have not just a local maximum, but an absolute maximum right there at x equals 50. So to answer our question, the area, a of x, is maximized for x equals 50. Now, we're not quite done because, remember, it said to find the dimensions x and y that maximize the area. We got to find y too. But remember that y was equal to 50 minus a half of whatever x is. So knowing x, we can also find y now. It's 50 minus a half of 50, which is 25. So the answer is this. Your size or dimensions of the enclosed region should be x equals 50, y equals 25. That gives a maximum area of 50 by 25 equals 1250 square feet. And that answers the question. Before we move on, I want to point out that this 1250, that's bigger than the one we got just by hit or miss on the previous slide, where I believe it was, we did what 60 by 20 feet, and we had 1,200 square feet of area. You can actually see this is better than that, and in fact, as we've proved here, this is the absolute greatest area you could possibly enclose using all 200 feet of your chain link fence. So this example is pretty typical of the kinds of examples that you're going to see in this section and that you'll see maybe in the future if you continue to go further with calculus, whether that's in your education or in your career. These problems are the thing that's common to these problems is that they really come into two pieces. In the first part of the problem, you've got to find a function to take the maximum or minimum of. And that involves some creativity. You might have to come up with some kind of constraint. You use the information and figure things out, all to find a function whose maximum or minimum would solve the problem that's posed at the beginning. And then once you find that, that's sort of like the creative part of it. Once you've found that function, then you start to use the techniques. You're kind of turning the crank after that, using the techniques to find max and min that we talked about earlier in this chapter. So really the only new thing we're talking about in section 4.5 is this creative part, where you really have to think a little bit to analyze the problem and come up with a function to maximize or minimize. The text calls that function an objective function. Let's take a look at another example. In example 2, the situation is this. There is a 1 mile wide river in blue, and this is the aerial view, so you're looking down at things. It's a perfectly straight river, 1 mile wide, like maybe a straight section of the Mississippi or something. On one side of the river is a power plant, and then on the other side, and then 5 miles down the river, is a factory. And your job is to run a power line from the power plant to the factory. And of course that's going to cost money, and you're planning this thing. And that power line has to run partly underwater and then partly above the surface. It goes under first and then above the surface. And here's the information that you have available to you. This underwater cable, it cost $50,000 per mile. to construct. Whereas the cable along the surface, going along like this, that's a little cheaper. It's $40,000 per mile. And the question is, given this information, to find a configuration that minimizes the total cost. What we want to do is find an X for which the total cost of construction is minimized. And the X here is given in this picture. There's a point A directly across the river from the power plant. And then measuring from A, we go down a distance of X. And that marks the point where the underground cable hits the above ground cable. And the cable continues to the factory. So the question is, what should X be? How many miles should it be so that the total cost of laying this cable is minimized? So before we start working on a solution of this problem, let's play around with it a little bit. One option that you could do is you could say, well, the underwater cable is the most expensive, so I want that to be as short as possible. I'm just going to go straight across 1 mile with underwater and then continue down 5 miles to the factory on the surface. And in that case, your X is equal to 0. Your cost then would be, let's see, the underwater was $50,000 per mile. You only want a mile, so it's $50,000 for underwater, plus 5 miles for the surface cable at a cost of $40,000 per mile. So that's 5 times 40,000, and the total cost is $250,000. On the other hand, you might say, well, I'm just going to take the shortest distance, the straight line distance from the power plant to the factory. Shorter distance means cheaper, maybe, and you just go straight across like that. And in that case, X is 5. The distance from A to this point is 5 miles now. And what is the cost? Well, that distance, the length of the cable, is the hypotenuse of this right triangle with legs 1 and 5. So by the Pythagorean theorem, the distance of the length of underground cable that you have is the square root of 1 squared plus 5 squared. And it's $50,000 per mile. So the total cost here is 50 times square root of 6, which is approximately $255,000. So even though you went a shorter distance, you were actually a little bit more expensive going straight across. And that kind of makes sense because even though it's shorter, it was more expensive per mile. So this problem is saying, maybe there's some happy median between x equals 0 and x equals 5, like coming up like this. There's some value for x where you go across the river, you hit right there, x miles from point A, and then continue here, where the total cost is minimized and it's less than what you're getting here. That's what we're trying to do in this problem. So let me get rid of this stuff on the bottom here now that we've illustrated it. And we're looking at our problem. The power plant and the factory are located on the opposite banks of a river as shown. And a power line must connect them, partly underwater, partly on the surface. The underwater cable costs $50,000 per mile. The surface cable costs $40,000 per mile. Your job is to find the X for which the total cost of construction is minimized. What should this X be? Let's get to work on that. That's going to involve a couple of things. If we're going to compute the total cost of construction for laying this cable, we've got to figure out how far we went underwater and multiply that by 50,000, and then how far we went along the surface and multiply that by 40,000 and add those together. And that's going to give the total cost, which is what we want to minimize. So let's get to work on that. The length of this underground cable would be, well, we could get it with the Pythagorean theorem because that length is the hypotenuse of this right triangle whose legs are 1 and x. So the length of the underground cable by the Pythagorean theorem is square root of 1 squared plus x squared miles. Now, what about the length of the surface cable? That's how far you're going along the surface from here to here. Well, the distance from A to the factory is 5 miles, and you're not using these x miles in the surface cable, so the difference is 5 minus x. That's the number of miles of surface cable that you have, 5 minus x miles. So putting these together, here's the total cost. You have to, for the total cost, you have to take the length of the underground cable and multiply it by 50. And we're using units of thousands of dollars here, so $50,000, 50 times the length underground, plus, and then for surface cable, the length of surface cable is 5 minus x. It's $40,000 per mile, so that's a 40 times 5 minus x. So let's call that a cost function c of x. For a given x, the total cost of construction is c of x equals 50 times square root of 1 squared plus x squared plus 40 times 5 minus x, $1,000. Cleaning that up a little bit, c of x is 50 square root of 1 plus x squared plus 200 minus 40x when you distribute the 40 through. So that's a function of x. That's c of x, and that's the function we want to minimize. We want to find the value of x that gives an absolute minimum of cost. So we want to minimize this function on the interval from 0 to 5. Now it's from 0 to 5 because x could be 0, as little as 0, or as big as 5. Now class, at this point, this completes the creative part of this problem. We've cooked up a cost function and we said we want to minimize it on this interval. At this point, from here on out, it looks a lot like, almost identical to, the kinds of problems that we were handed in section 4.3. Here's a function, find its absolute minimum on this interval. So on the next slide, we're going to do that. So going forward, I'm just going to copy over this line in the next slide up at the top. We've got a cost function. C of x is 50 square root of 1 plus x squared plus 200 minus 40x. We want to minimize that on the interval from 0 to 5. Well, you know you're going to take a derivative, so before we do that, let's just convert that radical to a power because you're expecting to use the power rule here. And now we can find our derivative. Constant multiple rule brings the 50 here. The 1/2 comes down times the function 1 plus x squared to the power of 1/2 minus 1, which is negative 1/2. Then times the derivative of the 1 plus x squared, which is 2x. Then plus the derivative of 200 minus the derivative of 40x. So cleaning that up a little bit, c prime of x is 50x over square root of 1 plus x squared minus 40. And we want to find the maximum of c of x. So we know that's going to happen, well, actually either at endpoints or at a critical point. So we want to look for the critical points. Those are the values of x that make the derivative 0 or undefined. Now, there is no value of x that makes this undefined. Even if x is negative or 0, you have a 1 plus x squared that's a positive down there inside the radical. So you're not taking the square root of a negative number, nor are you dividing by 0. So there are no values of x that make the derivative undefined. So that means if we're looking for critical points, we got to find the values of x that make the derivative equal to 0. So to find them, we set that derivative equal to 0. And we're going to solve. First of all, bring the negative 40 over to the other side, then cross multiply. We can knock down those numbers by dividing both sides by 10. And okay, now we've got this radical equation we want to solve. We want to get x by itself. We're in a radical over here, and we could square both sides to get rid of that radical. So there we go. Now the 5x squared on the right is 25x squared. The 4 root 1 plus x squared, whole thing squared, is 16 1 plus x squared. Good, we got rid of the radical. Let's multiply that 16 through, and we can collect like terms. We could subtract a 16x from both sides, and we get 9x squared equals 16. X squared is 16 over 9, and taking the square root of that, we get x equals 4/3. Well, technically, it should be x equals plus or minus 4/3, but remember the interval is from 0 to 5. So we're not using the negative root here. So 4/3 is our critical point. Okay, just one critical point. So if we're going to have a maximum, it could occur at that critical point, but we don't know until we check. So let's first of all use the first derivative test. So we're looking at the interval from 0 to 5. I've got that plotted. Here's our critical point of 4/3. And we're going to look at the sign of c prime of x. Let's see. Why don't we take a test point of 0? If you plug in 0 to c prime, 50 times 0 over this is 0 minus 40. That's definitely negative. So c prime is negative there. And then we can take a test point of, well, maybe 2 here. We could plug that into c prime. And that would be 50 times 2 over the square root of 1 plus 2 squared minus 40. And maybe you want to take out a calculator there. You can do it by hand, but a calculator would be quicker. You'll quickly find out that that's positive. So c prime of x is positive when x is greater than 4/3. So the graph of c of x was decreasing for 4/3, and then it started increasing again. And we have a local minimum right there. So the graph looks something like this, the graph of cost in terms of x. And you could see here you get an absolute minimum of 4/3 for cost. Now here, when we talked about finding the maximum and minimum value of a function on a closed interval, we actually plugged in the endpoints. That was part of our procedure. We don't need to do that here because we only had one critical point, and we figured out that we were decreasing then increasing. So the function had to go down and then go back up. Maybe if we were looking for an absolute maximum, we'd have to plug in these endpoints and find out which one is higher. But the problem here is just to find the absolute minimum, and we've got it right there at x equals 4/3. So, answer, make x equals 4/3. That's going to minimize the cost. So what you want to do is route your cable this way, where the cable on the other side of the river, going to the other side of the river, it meets at a point that's 4/3 of a mile from the point A over here. And if you do that, that's guaranteed to minimize cost. And you can actually compute the total minimum cost. You take that number, x equals 4/3, you plug it into your cost function, which was way up here. And it all churns out to be $230,000. That's the lowest possible cost you could get. Now, if you think about what we did on the previous slide, we were just playing around. We tried x equals 0. We got, what, $250,000? x equals 5 gave $255,000. This is lower by $25,000 than both of those. So if you're an engineer, your boss is going to be happy. You'll get a raise. Another example. This is another cost problem, a construction problem, and here it is. You need to build a shed that has an open front and a square base and contains a volume of 10,000 cubic feet. So here it is. It has an open front, so it's only got 3 walls on the right side, the back, and the left side. It's got a roof and a floor, and its base is square, so it's x by x. So you have to build this thing, and the volume has to be 10,000 cubic feet. And you're looking at the cost of construction supplies, and you figure out the roof is going to cost $10 per square foot. The walls, they're $8 per square foot, and the floor is $5 per square foot. So the question is, what dimensions, x and y, will minimize the total cost of materials? So again, x is the length and the width of the building, and y is the height. What x and y should you use so your construction costs are minimized? Well, in this problem, there's actually a constraint. Way up at the top, it stated that the volume enclosed in this shed should be 10,000 cubic feet. So the volume is length times width times height, which is x squared times y. Length times width times height is x times y. That's x squared times y. And that has to be 10,000 square feet. So right away from that, we could solve for y, and we figure out that dividing both sides of this by x squared, y has to be 10,000 over x squared. So neglecting cost for now, if you choose an x, you could let x be any value you want it to be, but then y has got to be 10,000 over x squared to make the volume equal to 10,000 square feet. Okay, that was just a constraint that I got out of the way because it was one of the first things that was mentioned here. Let's figure out what we need to minimize here. We want to minimize the total cost of material. So that tells us we've got to get creative and cook up a function that gives us cost. Now we'll rough it out here. The cost of materials would be the cost of the roof plus the cost of the floor plus the cost of the walls. And there are 3 walls here, so we got to include the cost of all 3 of those. Now each of these we should be able to figure out. Look at the roof. It's x by x square feet. So it's x squared square feet. And the cost is $10 per square foot. So the total cost of the roof is going to be 10 times the area of the roof. That's 10 times x squared. Moving on to the floor. Well, the floor is also x squared square feet, but it only costs $8 per square foot. So the cost of the, it only costs $5 per square foot. So the cost of the floor is 5 times the area of the floor, which is 5 times x squared. Then we have to add on the cost of the 3 walls. Now if you look at these walls, there's one on the right, it's x by y feet. And the back wall, it's also x by y feet. And the left wall is x by y feet. So each wall has an area of x times y square feet. And there are 3 of them, so the total area enclosed by those 3 walls is 3 times xy. And remember, the cost per square foot of the walls is $8 per square foot, so the total cost of the walls is 3 times 8xy. So the total cost of construction is 10x squared plus 5x squared plus 3 times 8xy. Collecting like terms, that's 15x squared plus 24xy. So remember, we want to minimize this cost, which equals this quantity. And we have all these techniques for finding the absolute minimum of a function, but that has to be a function of one variable for our techniques to work. And you'll notice we have a y in here, which is a little bit annoying. We got 2 x's, we got a y, so somehow we've got to get this to a single function of x. Now, you don't have to look too far to see what to do. Remember, our constraint gave us y equals 10,000 divided by x squared. So all we need to do is replace this y by 10,000 over x squared, and it's all x's at that point. So there we go. We got the 24x coming down here, and this y just got replaced by 10,000 over x squared. So good. Our cost function is now a function that has only x's in it, but we could clean it up by doing a little cancellation there. Cost is equal to 15x squared plus 240,000 divided by x. Let's summarize that. The cost is now a function we'll call c of x that gives the cost of materials. C of x is the cost of materials for this dimension x. For whatever x is, the total cost of materials is going to be 15x squared plus 240,000 divided by x. And this is the function we want to find the minimum of. We want to minimize this function, find the x that makes that cost as small as possible, and it's going to happen on some interval. And what's that interval going to be? Remember, we said x, it's a length, so it's got to be greater than 0. But then how big could x get? Well, x can get as big as it wants to get. If you look at this constraint function, x could be 10,000 feet or 100,000 feet or 1,000,000 feet if it wanted to. And then we get a corresponding y here that makes x times y equal to 10,000. You can kind of see that if x is really, really, really small, then y has to be really, really, really big to make up 10,000 cubic feet. And if x is really, really, really big, then x has to be really, really small. So that's the way it's working here. But x could be as big as it wants to be. So we want to minimize this cost function on the interval from 0 to infinity. Okay, we just completed the creative part of this problem where we built up our cost function that we want to minimize. And at this point, down at the bottom, it looks just like a bunch of other problems that you've already worked in section 4.3. Here's a function, find a value of x that gives the absolute minimum of it. So let's do that on the next slide. Summarizing what was just at the bottom, we've got a cost function, c of x equals 15x squared plus 240,000 over x. We want to minimize this on the interval from 0 to infinity. So we know that the first thing we want to do is hunt for critical points, meaning we have to take the derivative. C prime of x, if you differentiate c prime, you get 30x minus 240,000 over x squared. And let's see, critical points are going to be the values of x for which that's 0 or undefined. And right away it looks like if x were 0, c prime of 0 is undefined because you're dividing by 0. But notice that 0 is not even in the interval. It's not an endpoint here. X is greater than 0. So that's not a critical point that's in our interval. In fact, it's not even a critical point because it's not in the domain of c of x. You can't plug in 0 to c. So there are no values of x that make the derivative undefined that are also in the domain of c of x. So the other kinds of critical points are the ones where this derivative is equal to 0. And to find them, you take that derivative and you set it equal to 0. Okay, we got two x's. I think we could clean it up. We could multiply both sides of this equation by x squared to get 30x cubed minus 240,000. And after that, we could knock those numbers down a little bit by dividing both sides by 30. I'm sorry, not yet. Let's add a 240,000 to both sides. And now we can knock those numbers down a little bit by dividing both sides by 30. We get x cubed equals 8,000. Taking the cube root of both sides, x is the cube root of 8,000, which is 20. So there's our critical point. We just got one critical point here. So we don't want to be hasty and jump to the conclusion that that's our answer, that x should be 20, and that would give us the minimum cost, because remember, we haven't checked whether this gives us a maximum or a minimum. We'd be in bad shape if we had a maximum at x equals 20. We're looking for a minimum. So for that, we've got to use some techniques from Chapter 4. Let's try the first derivative test. So we take this critical point, we plot it on the number line, and let's see, let's take a test point in here. If x were for example, if x were 1, c prime of x would be 30 times 1 minus 240,000 divided by 1 squared, and that's massively negative. So c prime of x is negative on this side of 20. Now on the other side, you could take well, look at it this way. If x got really, really, really large, you'd have 30 times a large number minus 240,000 divided by a really large number. Well, just take x bigger than 240,000, and this quotient is less than 1. And then you're adding on this really big positive number. So you can see for really big x's, you're going to get positive. So taking any test value way out here, c prime of x is positive. So you put positives there. Aha! And look, now we have a local minimum right there at 20 by the first derivative test. And this says the cost function was decreasing until we got to x equals 20, and then it started increasing again. So we know we've got an absolute minimum right there at 20. Okay, so x equals 20 minimizes the cost. And remember, the problem asked for both x and y, and we knew from that constraint that on the previous slide that y is 10,000 divided by x squared. So if when x is 20, y is 10,000 divided by 20 squared, which is 25. So here's the way you should make your shed: 20 by 20 by 25 feet, and you're guaranteed to have minimum cost. Answer: use the dimensions 20 by 20 by 25, and you'll get a minimum cost of c of 20 equals 15 times 20 squared plus 240,000 divided by 20, and that's $18,000, which seems kind of high, but it would be higher if you used any other dimensions than the ones we got here.
That's probably enough for today. We'll stop here. We'll break optimization problems into two parts. Today was lecture 34A. Coming up will be lecture 34B, optimization problems continued, and we'll just work some more examples. Have a good day, and I'll see you next time. Goodbye.